Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our conversation about global, or I should say maximums and minimums, and we're going to talk about absolute extrema, those greatest maximums and least minimums, I guess you could say. So we've already talked about local maximums and minimums, which is a harder conversation to have. So now we kind of ease into something really nice, absolutes. So F is considered to be an absolute max, or it has an absolute maximum or a global maximum at C if f at C is greater than or equal to f of x for all x in the domain of our function. And that's the difference between absolute maximums and local maximums. An absolute maximum looks at the entire domain of the function. That's the critical difference. D being the domain of the function versus local maximums. They only look at a neighborhood, a local neighborhood about C. Likewise, f has an absolute minimum or a global minimum at C if f of C is less than or equal to f of x for all x, again, in the entire domain. So let's take a look at this example. Use the graph to state the absolute maximum and minimum values of the function. Now, it's very important to remember a maximum or minimum value must have an associated x value that's in the domain of your function. The domain of this function is not all numbers between 0 and whatever this number right here is, which I think is 1, 2, 3, 4, 5, 6, 7. It's not every number between 0 and 7. The domain of this function is actually including 0 but ending before we get to 7. It doesn't include 7. So that's going to be kind of important. So if you look through all the y values here, it's much easier for me just to ask what's the maximum or the tallest or the highest y value, the greatest y value, if you will. And most students will easily pick it out. It's this guy right here. Not a huge deal, right? So 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, so 4, 5. So we have an absolute max, which I call an A max, an absolute max at x equals 4, which was a weird looking x. X equals 4 of with a value. Maybe I'll say it this way: absolute max value of 5 at x equals 4. Normally I just write absolute max 4, 5. That's what I normally write. That's why I was having a moment trying to figure out how to write that. So, but you have an absolute maximum value of 5 at x equals 4. Well, that is not the hard part for students. What's the hard part is saying, by the way, there's no absolute minimum here. Because if you take a look at this, some people will say, yeah, there's an absolute minimum right here. And I would say, no, there's a value that's slightly below that over here. And you say, great, well then that must be our absolute minimum. And I would say, nope, there's a value below it right there. And you say, great, that must be our absolute minimum. And I'd say, nope, there's a point right there, slightly below it. You say, great, that's the absolute minimum. And I would say, nope, there's always a point slightly below wherever I shade. And you say, well, then the absolute minimum must be a height of 1. And I would say no, because that height of 1 never occurs for this function. There is no absolute minimum for this function because it never gets down. The y values never actually get down to this level here. They get close, but they don't get down to that level. And you cannot say, oh, therefore 1.01 is the minimum, because 1.001 is below that, and this function will achieve that value. And you can't say 1.001 is the minimum, because 1.0 with 1,000 more zeros and then a 1 is still in the range of this function. So that being said, there's no absolute minimum here. No absolute minimum. And that's really because this function is not continuous and there's not a closed interval. And that's something we'll talk about in a little bit. So let's recall a definition and theorem that we mentioned a while ago in our series of videos here. A function's continuous at a number a if the limit as x gets really close to a of f of x is equal to f of a. Otherwise, it's discontinuous. And also, in that kind of that same region of material, the following functions are continuous on their domains: polynomials, rational functions, root functions, trig functions, inverse trig functions, exponential functions, log functions. Now, why do I mention that? Why do I worry about continuity and then, again, continuity of functions? It's because of the extreme value theorem, not to be confused with the intermediate value theorem. The extreme value theorem is a very easy theorem to understand. If f is continuous on a closed interval, then f attains its absolute extrema on that closed interval. That is, you have some function that is continuous on some closed interval from a to b. So this is x equals a right here. This is x equals b right there. Because it's continuous, it must attain its maximum and minimum on that, its absolute maximum, its absolute minimum on that interval. Its absolute max occurs right here. Its absolute minimum, hard to say because of the way I've drawn this. There you go. Now, I say this to my students in class all the time. Theorems in calculus are actually really easy to understand, really terrible to prove. Theorems in algebra, really terrible to understand actually, but very easy to prove. This is one of those that's really easy to understand. You have a continuous function on a closed interval. It's going to reach its maximum and minimum on that interval. But the proof is well beyond the capabilities of any undergraduate level mathematics course. So we cannot do that here. I'm not even going to attempt it. So let's go ahead and concern ourselves with this function. Sketch the graph by hand and use your sketch to find the absolute and local maximum and minimum values of this function. We know how to graph a logarithmic function, and I'm going to go ahead and be somewhat rigorous with this. I'll graph in here a y-axis, which will also be our vertical asymptote, and an x-axis, which will also be our x-axis. And of course, that's usually at 0 degrees. So there's our x-axis that I can't seem to graph. There we go. And now I'll go ahead and just kind of sketch in here a logarithmic function. This point that I'm crossing right here, that's x equals 1/3, y equals 0. And then we're going to go to an x value of 3. So basically we want our output to be a natural log of 3. So something like that. Actually, it's probably, since that's 1/3, it's probably over here. Okay. But we're going to put a little solid dot there at 3. And again, this point is 3 comma the natural log of 9. We'll put a little solid dot there because that's where our interval is going to solidly end. It can get all the way up to 3. But remember, the natural logarithmic graph has a vertical asymptote at 0, so obviously you cannot plug in 0 to our natural logarithm there. As far as absolute maximum on this interval, you could see that it does achieve an absolute maximum at the point 3 comma natural log of 9. That's our absolute maximum. It will never reach an absolute minimum because it falls forever and ever and ever. So there's no absolute minimum. 2 examples in a row. I didn't mean for that to happen, but there you go. And remember, to be a local max or a local minimum, it cannot be an edge point on the interval. So therefore, this point right there is not a local max. In fact, this function does not have a local max. There's not a point on here that you could plot that's above other points on both sides. That just won't happen with this function. So there's no local extrema here. So that's a good example of being asked to graph a function and having to determine the absolute maximums, absolute minimums, local maximums, and local minimums on the given interval. This is not contradicting the extreme value theorem. The extreme value theorem told us, hey, we're going to get absolute maximums and absolute minimums if we have a continuous function. But there was one other condition. The interval had to be closed. And this interval is not closed. It's half open. So we're not going to get an absolute minimum here. Now, I'm not a huge fan of how-tos or recipes on how to do things. When I'm teaching something, when I'm reviewing something, that's totally different. But teaching something, I don't like to write down recipes. However, this is very traditionally done this way, even in calculus textbooks, so I might as well just do it. Given a function on a closed interval, and by the way, it should be a continuous function, I should say. So let me change that. Given a continuous function on a closed interval, find the absolute extrema. It has to be continuous because then we can use the extreme value theorem. So what we're going to do is evaluate the function at the endpoints of the interval. That's f of a and f of b. Those will be candidates for our absolute maximums and our absolute minimums. Then we're going to find the critical points for the function on the open interval. So in other words, find out where the derivative doesn't exist, find out where the derivative becomes 0. And then we're going to find the y values for those critical points. Well, that's why they're called critical points, not critical numbers. The maximum of all these values will be the absolute maximum for the function. The minimum of all these values will be the absolute minimum for the function. We are essentially using this theorem from our last video by saying, well, if we do have an extreme, a local extreme, so not the edges of our interval, but somewhere in between, right? If we do have a local extreme, then we know that extreme is a critical point. But we also know that not all critical points are local extremes. So we're kind of doing some overkill by looking at all the critical points, because not all critical points are going to be extremes. But this is how we cover all the bases. We know that if we do have an extreme, it will be a critical number or a critical point. So what we're going to do is just look at all the critical numbers and evaluate the functions for those y values or for those x values to find the critical points. So essentially you're just saying, okay, let me check the y values at the edge points and let me find out where the derivative is 0 so I can see if I have a local max or a min, and that might be the maximum for the entire function. Or perhaps you have a cusp like this, and that could be the maximum for the entire function. That's what we're doing. Continuity is critical here, by the way, but it's actually, now that I think about it, not so critical. Because even if it's not a continuous function, well, I'll erase that now. Even if it's not a continuous function, the critical points will still showcase. So we have something like this. Let's say it looks like this. The critical points, which this would be a critical point because the derivative doesn't exist there, would still allow us to see if that's a local or a maximum or a minimum. So no, I guess I don't need continuity of that function. So let's try that technique here. Find the absolute minimum and absolute maximum values for our function on the given interval. The interval is 0 to 5. I'll first start by checking the edge points. So I'll just build a table because it's a lot easier, x versus f of x. I'll look at 0. If you plug 0 in, you get 0 out, actually. If you plug 5 in, you'll get the square root of 5 over 27 plus 25, which is 52, whatever value that is. I have no idea. It's not a huge number though. But you can see that we have a candidate for an absolute minimum, right? That's the smallest of those two outputs. So that's a candidate for an absolute minimum. Now we're going to take the derivative of that function. Well, f prime of x, it's a quotient, so we're going to use the quotient rule. I'm just going to call this x the 1/2 because that's what I would prefer. The derivative of the numerator is 1/2 x to the negative 1/2 times the denominator, 27 plus x squared, minus the numerator, x to the positive 1/2 times the derivative of the denominator, all over the square of the denominator, 27 plus x squared squared. And we want to know, when does this not exist, or when does it become 0? Well, one thing I'm going to do here is I'm going to multiply numerator and denominator by x to the 1/2 power. before I even begin. Oh, actually 2x to the 1/2 power. If I do that, your denominator will be 2x to the 1/2 times 27 plus x squared being squared. The numerator will be 27 plus x squared minus 4. Let's see, that would be an x. The 4 came from 2 times 2, by the way. And we'll have x times x, or x squared. Let me just double check my mathematics on that. I'm multiplying by x to the 1/2, so it becomes an x times an x. That's an x squared. Multiplied by 2, that's 4. Yes. And so this cleans up a little bit to 27 minus 3x squared all over 2x to the 1/2, 27 plus x squared squared. That denominator will not exist, or sorry, the function that's derivative will not exist at x equals 0, but we already have that listed as a point, so I'm not going to bother with that. The derivative will be 0 though, so f prime will equal 0 when 3x squared is equal to 27, or in other words, x is equal to plus or minus 3. Negative 3 is not in our domain, so I don't have to worry about that, but the 3 is. So plugging in 3, we get the square root of 3 over 27 plus 9, which is 36. And now I just need to see, of all of these y values, what's the greatest and what's the smallest. And those would be my absolute maximums and absolute minimums. If you take a look at this, obviously 0 is the smallest y value, so that's our absolute minimum point. And then you have to worry about the square root of 5 over 52 versus the square root of 3 over 36. And I just grabbed a calculator just to do it, and this would be the smaller number between the two. So root 3 over 36 is actually the larger. That's the absolute max. So that's the absolute maximum value of that function. Now, kind of an interesting little point here is that we could actually plot these points to kind of get an idea of how this function looks. Let me just tell you, that would probably be very difficult to do normally. So this is 0, 0. This is 3, 0.048. So I'm going to go 1, 2, 3, 0.048. I'll just say is right there. And 5 is at 0.043. So it looks something probably like this. Notice you probably would never be able to graph that by hand otherwise, but that's likely sort of what the function looks like. It's not the best, but it probably sort of looks like that. But just give you a heads up, that's actually where we're going to go. We're doing all this to get more and more accurate graphs of our functions. Let's try another example. So here we're asked to find the minimum, absolute minimum, and absolute maximums. By the way, I do want to say some people call these just the minimum and maximum values. So if you see that in your homework, they really mean absolute or global minimum and maximum values. In our interval, we were handed 0 to pi over 2. Not a big deal. If somebody asked me to graph this 2 cosine of t plus sine of 2t by hand, I'd probably scoff a little bit maybe. But it's mainly because you don't want to graph a combination of functions by hand. But in calculus, you can start to. So let's see, let's go ahead and evaluate the function at the edges of the interval. So x versus, or sorry, it's t actually. T versus f of t. The interval goes from t equals 0 to t equals pi over 2. I'll just plug those values in. At time 0, sine of 0 is 0, cosine of 0 is 1, so that's 1 times 2. And then at time pi over 2, cosine is 0. At time pi over 2, sine of 2 times pi over 2 sine of pi, that's actually 0. So it's pi over 2 comma 0. Of those two values, we have an absolute max at 2 and an absolute min so far at 0. But that doesn't mean they're going to stay the maximums and minimums. Let's go ahead and take a look at the derivative. The derivative is going to be a negative 2 sine of t. Let's see, plus 2 cosine of 2t. That's just the chain rule that I did there. And that exists for all real numbers, so there's not going to be an issue with the domain. But we do want to solve to find the other critical numbers, solve f prime is equal to 0. And that would occur when, let's see, sine 0 is equal to, I'm just going to divide everything by 2, a negative sine of t plus cosine of 2t. This requires us to remember our trigonometric identities. Cosine of 2t can be written as 2 cosine squared of t minus 1, or 1 minus 2 sine squared of t. I'm going to choose that latter one. And this is why I also say to students that knowing all of trig is so incredibly important, because problems like this just creep up. You're working on an exam, and if you didn't study all of your trig identities, you're pretty much done. You got to know this stuff. It's not like your instructor's going to be like, oh, you know what? Here's a whole trig textbook while you take this exam. You just got to know this stuff. Anyhow, this becomes 2 sine squared of t plus sine of t minus 1 is equal to 0. We'll try to factor this. I think it does. 2 sine of t and a sine of t equals 0. 1 and a 1, and that's probably going to be a plus, and this will be a minus. There we go. That's the factorization. So sine of t is either equal to a half, or it's equal to a negative 1. Well, the negative 1's easier to talk about. Keep in mind the domain. We're only dealing with angles in the first quadrant there, 0 to pi over 2. Sine is not going to become a negative 1 because on that interval, because sine becomes negative 1 at pi. So, or sorry, not pi, at 3 pi over 2. So that's outside of our interval, so we don't have to worry about that. But sine becomes 1/2 at pi over 6, and also 5 pi over 6, but that's outside of our interval. So pi over 6 is the winner there. And then you're going to evaluate these functions, or f at pi over 6. Twice the cosine of pi over 6 is, let's see, 2 times the square root of 3 over 2, which is square root of 3, plus sine of twice pi over 6 is the sine of pi over 3, which is root 3 over 2. So this is going to be 3 root 3 over 2. And let's say that you don't have a calculator. How do you compare 2 to 3 root 3 over 2? Easy. Square them. If you square them, the larger, because they're greater than 1, when you square them, the larger will be the larger value. So square of 2 is 4. The square of that would be 9 times 3 over 4, or 27/4, which is greater than 6, honestly. And so 3 root 3 over 2 is greater than 2. So this right here is our absolute max, and this is our absolute min. And if you were to want to graph that function, I suppose you could, just out of curiosity, right? We know at time 0, the height is 2. 1, 2. At time pi over 2, the edge of the interval, the height is 0. And so that's our absolute minimum. And time pi over 6, which is like a third of the way through this interval, it is a height higher than 2. So it might look something like this. That's pretty good. All right, let's see what we have coming up next. Find the absolute minimum and max. So it's the same question over and over again, right? I just want to drive the point home. Check the edges, take the derivative, check for critical points. So now we've got a good rhythm going. I'm just going to quickly do this instead of taking my time. If you plug in a -1, you'll get natural log of 1, which is 0. If you plug in a positive 1, you'll get natural log of 3, which is greater than 0. All right, now I'm going to take the derivative. F prime of x is derivative of natural log is 1 over its argument, x squared plus x plus 1, times the derivative of its argument, 2x plus 1. And just letting you know, that denominator will never become 0 because the discriminant is negative. So there is no way that's going to become 0. So I then So that basically means the derivative will exist. It always exists. And then I'm going to go ahead and set the derivative equal to 0. And that just means x is a negative 1/2. So that's within my domain. So I'll need to evaluate this at negative 1/2. That would be 1/2 plus 1/4, which is 3/4, natural log of 3/4. Okay. And of those values, the natural log of 3/4 is actually less than 0, so that's the absolute minimum. The natural log of 3 is actually greater than 0, so that's the absolute maximum. There you go. I don't need a calculator for that either. Pretty good. And I suppose that I could draw out, say, let's pretend this is x equals -1. Here's x equals 0. Here's x equals +1. At -1, we have a height of 0 for our function. At x equals 1, we have a height of natural log of 3. Let's just say it's up there. And at time -1/2, we have a natural log of 3/4, which is less than 0. So it might look something like this. It could look like that. Not sure. And as a final example, find the max and min of this function, period. And this function has an implied domain. The implied domain is built from the argument of that radical, the radicand itself. We need x minus x squared to be greater than or equal to 0. That's just how it's going to work. And so that means we need x times 1 minus x to be greater than or equal to 0. If you plot those numbers on a number line, 0 and 1, when I say those numbers, I mean where those turn into 0. And test points, test a point like -10. You'd get a -10 here, times 1 minus a -10, which is a positive value there, and you'd get a negative number over here, which is not what you want. If you try a number like +10, well, you'd get 10 times 1 minus 10, and that's a negative number, so you don't want that stuff over there. If you plug a number like a half, 1/2 times 1 minus 1/2 is positive. And so, winner, winner, chicken dinner, our domain is 0 to 1. And now, we just need to find the absolute maximums and minimums. Building our table of values, it's just the same thing from this point forward. I just wanted that example this example for that. So if you plug in 0, you get 0. You plug in 1, you get 0 as well. There you go. And then f prime of x, derivative of the first times the second, plus the first times the derivative of the second. And remember, that's a chain rule going on, so times 1 minus 2x. Double check my mathematics. Yep. And you know this is undefined at 0 and also at 1, but that's okay. And now we'll go ahead and solve f prime is equal to 0. That means that we want to solve negative root x minus x squared is equal to x times 1 minus 2x all over 2 root x minus x squared. I'm going to multiply both sides by a negative because I really dislike that negative over there. So I'll just do this. It's a root x minus x squared is equal to x times 2x minus 1 over x minus root x minus x squared. Multiply both sides. Oh, by the way, I didn't mean to write that x down there. Sorry about that. It was supposed to be a 2. Multiply both sides by 2 root x minus x squared, and you get 2 times the quantity x minus x squared is equal to 2x squared minus x. You get the whole idea, right? You get, let's see, this implies you have, I'm kind of going quickly, I apologize, 4x squared minus x minus 2x is minus 3x. Is equal to 0. Double check my mathematics. Add. Yep. So you get x times 4x minus 3 is equal to 0, or in other words, x equals 0, x equals 3/4. So we're going to have to check x equals 3/4, which is in our domain. And again, I know I went kind of quickly here, but that's just algebra, so I just didn't want to take my time with it. And you'll get 3/4 times the square root of some positive number. That's all I care about. It's 3/4 minus 9/16. And that's 3/4 square root of 412 3/16. Or in other words, 3√3/16. And that will be our absolute max. And this one has two absolute minimums. Both these values are actually absolute minimums. Because a function can have two absolute minimums. They'd have to be the same y value, but it's totally fine to have two absolute minimums. There you go. All right, we're done with this video, and I do apologize for rushing through that last one. It's just close to dinner for me, and I get edgy at dinner. There you go. All right, so I will see you in another future video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.